Warning: potassium nitrate is a strong oxidizer. Ammonia is corrosive and irritating. Hi guys, here is MIH. As you guys may know, making nitrates have always been on my top tier list of achievements, partly because nitrates are hard to obtain in my local area, and partly because nitrates are well known to be hard to synthesize from scratch. I have already attempted the Oxford process, the link is in the description, and failed, although I plan to try it again shortly after. The Oxford process is essentially ammonia being oxidized by air in the presence of a catalyst, and this certainly relies on a complicated airtight setup and extremely high temperatures. As you can see in my old video, I'm certainly not very good at this. Instead, I like to do everything by electrochemistry whenever possible, because it doesn't need special conditions and it is very powerful. Fortunately, scrap science afforded me the inspiration of making nitrates by electrolysis. A big shout out to his video on making potassium nitrate, which is in the description, and to the Science Madness forum that came up with the idea. Just for a recap, I will briefly go through what scrap science did. He set up an electrolytic cell with an anode compartment and a cathode compartment, separated with a paper diaphragm. Ammonia solution along with some copper carbonate catalyst was added to the anode side, and both chambers were filled with potassium hydroxide solution. Using a low-carbon steel anode and a copper cathode, he electrolyzed the solution at a current of 0.2 amps under ice bath and retrieved the nitrate by boiling down the anolyte. I basically followed the process, but with a few slight modifications to suit my working conditions. After keeping all these in mind, we can start our experiment. First, about 2 grams of anhydrous potassium carbonate was measured out and dissolved in about 25 milliliters of water. The exact amount isn't critical here. I swapped potassium hydroxide for potassium carbonate because I got it on hand and it should work as well. Then we will make our cathode compartment. It is basically a PE plastic reagent bottle with a bunch of holes punched on the sides. It is then wrapped in a layer of regular printer paper, secured by a piece of PTFE tape. I filled a small beaker, which is the anode compartment, with the potassium carbonate solution, and fitted the bottle in. It floated on the solution, and as I added more solution inside it, it gradually sank. Next, we'll prepare our ammonia copper solution. I measured out about 0.1 grams of basic copper carbonate and added about 5 milliliters of 25% ammonia solution. Other copper salts like copper sulfate should work, but I haven't tried it out yet. I stirred the solution using a pipette, and the copper carbonate dissolved, forming a dark blue solution. This is the characteristic color of the tetraamine copper complex ion. Here we have our cell already set up, with a copper cathode in the vial and an iron wire anode in the beaker. I gradually added in the ammonia copper solution to the beaker, and the electrolyte turned to a beautiful blue color. As I turned on the power supply, the cathode emitted a lot of bubbles. The video quality was very bad, so you guys probably can't see it clearly. The catholyte was slightly blue because some of our copper catalyst transferred to the cathode chamber, which indicates that the reaction is working. The iron wire anode didn't bubble much at all, which is another good sign. I then placed the cell in my tray of ice-cold water, which will serve to cool the cell when it's running. In this shot, the cathode was clearly bubbling a lot, and the little bit of copper metal has already deposited on the electrode. We're several hours into the run, and it seems like that the cell resistance is incredibly high. Despite we had 12 volts, we only have around 0.07 amps running through the cell. Upon further inspection, the lower part of the iron anode corroded away. However, this should not be the major cause of our high resistance. After a few minutes, I took the cell apart and realized why. The paper membrane was heavily contaminated by some yellow particles, probably iron hydroxide. I only punched 8 holes, each about 1 millimeter in diameter on the side of the bottle. The holes are easily blocked by those tiny particles of iron hydroxide, which increases the resistance by a lot. I then modified the vial and punched more larger hole through it. Here you can see that it has 24 holes that are much larger than what we had before. I then wrapped another piece of paper onto it and put it back into the cell. Since the iron wire anode broke, I swapped it for a piece of copper to see if it works. It turns out that copper cannot withstand being the anode and corroded away. A lot of pale blue precipitate formed on its surface, probably copper hydroxide. However, this extra copper may replenish the copper catalyst that we put in at the beginning. I then swapped the anode again for stainless steel, and this time it seems to work. I left the cell running for a while, and the anolyte seems to turn from dark blue to slightly green. The current rapidly rose to about 0.8 amps. Here is a closer shot of the cell. The copper cathode is bubbling very vigorously, and the stainless steel anode was also bubbling slightly, but not even close to what the cathode looks like. Our cell is likely still fine and still producing nitrates. After 2 days, this is what the cell looks like. A lot of brown iron hydroxide precipitates appeared. Although it looks bad, our electrolyte is probably still fine because the current still holds at 0.25 amps. Make sure to always swap fresh ice bags every few hours to keep the cell chilled to 0C. I didn't do this very frequently, so some loss of yield is to be expected. Not long afterwards, I stopped the cell and took everything apart. The copper cathode didn't rust a lot, and it was covered in a layer of black copper deposits, which is totally fine. The upper part of stainless steel anode showed slight corrosion, but the part immersed in the electrolyte held up pretty nicely. When we look at the paper membrane, it was very dirty and covered in iron hydroxides. However, it didn't break, so it probably performed its job well enough. And finally, our electrolyte. There are not much catholyte present, and it showed a murky blue-green color. I wouldn't need this, so I discarded it. The anode was slightly more in volume and has a bunch of iron hydroxide suspended in it. I added some water to dilute it to about 50 milliliters and let it sit there undisturbed. After about an hour, most of the insoluble junk sank to the bottom, and the upper solution was crystal clear, although a bit yellow. Although I know yellow chemistry is as well a bad sign, it didn't really stop me, and I proceeded pouring the upper layer into a petri dish and let it crystallize. The solution probably has a slight amount of chromates in it, which was from the chromium that corroded off the stainless steel anode. This is probably why scrap science preferred a mild steel anode instead of a stainless one. However, I don't think this will significantly impact anything at all. Alright, here we are after a week. All of the water evaporated away, and we are left with some light yellow crystals in the petri dish. To test if those crystals are actually potassium nitrate, we do a simple test. Using a spatula, I scrape off a little bit of the crystals and place it inside a test tube. I then add a little water to dissolve it. Then I pour some concentrated sulfuric acid in the test tube. A lot of bubbles formed, which was the leftover potassium carbonate reacting with the acid to produce carbon dioxide. I then throw in a small piece of copper. If there are nitrates in the solution, we should see bubbles of nitrogen monoxide forming on the surface of the copper as it is oxidized by the nitrate. Apparently, no bubbles were forming. I heated the solution to boiling using a blowtorch, but there are still no bubbles. Unfortunately, this test for nitrate turns out to be negative. However, I don't want to end this project just like this after getting nothing. So I decided to dump all of my product in some sulfuric acid and throw in a piece of copper just like last time. After letting it sit for a couple of hours, the copper actually tarnished surprisingly, indicating a reaction. I guess that is now a positive result maybe? But anyways, I probably wouldn't repeat this process again because it just produces too little nitrate in one run. Also, it is way too labor intensive to keep the cell chilled to 0C. I would instead revisit the Oxford process for making nitrates. Nonetheless, the project was a successful proof of concept. See you next time!